All right, welcome everyone to our training from data to insight, building impactful visualizations for better communication. We have some great speakers for you today. If we can go to the next slide. I'll do a bit of introduction on why are we hosting this training. So this has been part of a series of trainings we've put on to further series is strategic imperative number 4. I'm on the committee that's helping further that initiative. And from that, we're going to be doing a series science illustration contest, which should be opening this week. So you'll be getting an email about that to let you know what's going on with that. So usually series does the photo contest. We're doing something with science illustrations this time. So we're really excited to be able to do this to help further our ability to communicate our science to people outside of series. So that contest hopefully will be opening this week, and that'll close in late April. So keep an eye out for that if you'd like to participate. And then all of the trainings that we're doing, including today's, the slides and recordings, are being hosted on our resources webpage. And so you can get to that information and keep an eye on all of the different resources we have for you for improving your communication to other scientists. Today, this is what we'll be talking about, more focused on data visualization. So first, Hillary will talk about lessons and opportunities from Science on a Sphere. Kathy will talk a lot about visualizations for science. And then Eric will host a hands-on visualization exercise. And any questions, answers, feel free to put any questions along the way in the chat, and then our speakers can answer after they get to the end of their respective sections, except for when Eric's doing hands-on stuff, feel free to speak up as things come up. All right, Hillary, you want to get us started?
Certainly. Yeah. Thanks, Jessica, for inviting me. So I'm going to try to go through this really quickly because I'm not necessarily giving you advice on how to make data visualizations as much as I'm letting you know about some of the resources here in the building, for example. So I'll be doing a brief recap of best practices in color bars. After, if you want to go into more detail, Chelsea Thompson did a great talk on the last training, so I recommend going to that. SOS project platforms and catalog, using SOS Explorer to initiate engagement while you're doing public talks, presenting data to audiences. I have a tip or two on that, and adding your data to the SOS dataset catalog. So color bars aren't trivial by any means. If you want to get deep into the use of color, hue, luminance, again, I recommend watching the first training in the series where Chelsea Thompson of CSL describes it in detail and also provided some book recommendations. But I decided to provide you with a few helpful shorter articles and websites that helped me, and these are in the bottom right-hand corner of the slide. But briefly, the 3 different data data types for color palettes used in visualization are categorical, which is also known as qualitative. I don't know a lot of people in this building who have a lot of qualitative data, but I'm sure there absolutely are. Divergent, which emphasizes extremes or a midpoint of 0, like an anomaly data set. And then sequential is common in, for example, Science on a Sphere data sets that we use. A depiction of a simple color scheme for each is indicated up here in the upper right diagram. I got this from the Data Wrapper article. They're linked at the bottom. So moving back to the sequential example, the problem with the typical rainbow color scheme is that it's not consistently or linearly luminous, as you can see with the grayscale graph there. This sequential data set in rainbow looks like it goes up, then it goes down. It's best to keep the luminance linear, as the example with the sequential up there in blue. And like I said, the Data Wrapper article that I linked here goes into how best to choose between sequential and diverging, because I think those are not always so obvious. Certainly when you're trying to show extremes, it's nice to have a diverging. Great. So that is my brief recap. So Science on a Sphere and SOS Explorer, these are the platforms that were invented in this building, and folks that you may know or not know, at least at NOAA Boulder, were the inventors, and also we are the headquarters of the Science on a Sphere platform. An estimated 22 million people see Science on a Sphere every year. And in the past 6 years or so, we've been able to increase that number, seeing our a number of people seeing our data sets by releasing the free SOS Explorer, both mobile app and the Windows application. So everything shown here that is a virtual flat screen is SOS Explorer. This is what we call the big ball, Science on the Sphere. There's one here in the NOAA Boulder office, as well as at CU's Fisk Planetarium. If you're interested in learning how to present on it or add your data, feel free to contact me, and I'll go into a few more details on that in a second. So the data catalog consists of more than 500 dynamic and static visualizations of Earth science data, typically global, 40 of which are near real time. We also have past observations as well as models that forecast the future and space science. We also have art and movies. Your data can be in here too. And we'll talk about that more in a minute, but you can see that the data can be visualized in different ways on the sphere. In particular, for example, the sea level rise simulation here shows the difference in 30 years of sea level, not necessarily globally as on the coasts. We've done that before. It's really hard to show that sort of change as being something that has changed a lot. So this one is more like water in a bowl, and it's expanding and increasing, and you can kind of see it going up and down. So the sky's the limit in some ways, as long as you can be creative and figure out how to wrap something around a sphere. In addition to the 180 or more SOS International installations that are currently up and working, as well as SOS Explorer, we also serve up free data to other platforms, including OpenSpace, digital planetariums, NASA's Earth Information Center, and other spherical platforms. And there are actually quite a few. Using SOS Explorer for public engagements, one way I recommend engaging students or the public with your data is by using SOS Explorer or Science on a Sphere, if you're here, in the building, and just talking about things at a higher level before diving deep into your specific research. So for example, let's say you work on climate change research or greenhouse gases. You may first want to get students centered around the idea of carbon dioxide sources around the world. So I forgot that you could hear I don't know if you can hear my clicks, but this is one of the data sets. This is actually a NASA GEOS 5 data set from 2006. It's a model of carbon dioxide, mostly sources, but of course, distribution around the globe. And so I was just sort of trying to let you know the different ways in which you can interact with that data using SOS Explorer. So if you want this lovely capability on your computer because you're doing a great talk, for example, at the local bar, I did one of those once at a brewery. That was super fun. Or you're doing a presentation for students in a classroom, I think it's a good idea to get the data sets and the Windows application on your machine if you can. Check it out. Maybe there's a way to engage people in that way. On the other hand, we also have mobile. And of course, if you give our data sets, if you give us your data sets, they might also be on all these platforms. So I think those links have been posted in there, but if you want to go back and look at the talk later, you will see these links that I added. So one thing I wanted to just go into before finishing up today is just like math, I don't know if you've ever experienced being out at dinner with people and everybody has a different way of doing math in their heads. Um, Everybody absorbs information differently. Now, when you're doing a PowerPoint presentation or you're taking in a PowerPoint presentation and there's words and there's graphs and there's visualizations and you're listening to a presenter, sometimes it's all a little bit too much. So, understanding data, just wanted to, even if there's scientists in your field of study, it takes time. So the way that I assist in doing this is by allowing folks to silently take in a data set. For this data set as well, actually, I oftentimes will put it up, ask folks to read the legend, and then, of course, on Science on the Sphere, I can allow them to stand up, walk around the room, and make observations and report back. So that's much more of a learning experience than, for example, getting your data out there. But I think it's a really good thing to remember because I've sat through so many presentations on things that I know a lot about, and I still wasn't able to take in the graph that they had on the screen while they were talking. So I do recommend allowing folks to absorb it in a little bit more time. And finally, if you want to contribute to the SOS Dataset Catalog, I think I may have gotten across that it goes to a lot of people. We do offer our data free to any platform that is spherical. There is my email address. You can just Google content creation guidelines if you want to know a little bit about the way that we accept data. But this map is kind of a small or a brief example of that we do a 2x1 equilateral cylindrical equatorial cylindrical equidistant projection. And it might be a still image, it might be a series of images, or it might be a movie, or it could be a video of a series of images. But you can contact us and we will help you out. So thank you. Kathy, you're up.
Okay, yeah, so I am going to present semi-random concepts for improving your science communication via plots. Next. So I've been working at Series CU for over 30 years. So I have a lot of background in the field. I am not an expert. I've just been here a while, though I have picked up stuff on the way. So I assume that's why Jessica asked me. And so you can consider this a bit of a beta talk, but I think it'll be useful. Next slide. Okay, so the first thing you need to do when you're considering making visualizations is distinguishing between the different audiences, because that will impact how you create your visualizations, your images. Next slide. All right, so the different audience types, at least how I looked at them, are first personal use. So there you want to be able to produce images that are quick to produce, where they're flexible. You can try different things out. You want to be able to have enough info to collaborate, but you don't need to explain it in gory detail to anybody. You don't have to worry about the, dotting your I's and all that. The next one is publications. Those need to be accurate, clear, and true. And you'd like to be able to reproduce them because, you'll be asked to do that. And they're probably they can be taken offline. People tend to look at them in papers, so it's very important you get those right. Posters, there you want them readable, and there you probably want to avoid the text. So you want your plots to tell the story. So you want to make them very clear, very readable at different distances. You want to have most of the information on the plot itself, not so much on the posters. So you might have bigger captions. Scientific talks, you want them readable at a glance. So from up front or in the back of the room, you want to reduce details as much as possible, but still give the story. So you want everything. So if you glance away for a bit, somebody watching, you want them to be able to pick up where you are and figure out what plots are and figure out the important details right away. So general science audience, similar, but you avoid more of the jargon, focus on the storytelling. General public, you get easier, more clear, less jargon. And children, of course, simple, fun, and concise. Okay, next slide. So personal use, as I said, you want to be able to do quick visualizations. You want to have the data saved. So you don't want to have to keep running your code to produce the data that you're plotting. You just want to save that. And there's a lot of interactive tools you can use that'll help you create the kind of plots you want. Some of them are application-based, like NC View. Some of them are command-like based, like grads. And they all have the ability that you can try stuff out, basically. So that makes it easier to create slides as you're coming up with your ideas. On the web, you can do some of this stuff too. There are pages where you can upload your own time series or data. There's also places that have a lot of different plots, and it's very useful to kind of see what's out there, to see if somebody has the kind of plot that might be helpful to present your data in the best way. Without, of course, stealing it, but use the features of it. Like I said, interactive web pages. Sometimes you can upload data, but you can also look at data similar to what you have and try different things out. And of course, you want to make your plotting code, if you have it, flexible, so you can, again, try stuff out. Next slide. Okay, so since I'm from PSL and NOAA, I decided to do an advertisement for some of our web pages, or you can try this stuff out online. So this is a time series page. I'm plotting sea surface temperature, like NINA 3.4 versus precipitation in the tropics, where there's a relationship. So here I tried 2 different plots together on the top left, 2 different time series, I mean, and you can see they're related, but it's a little hard to tell how they coexist. So on the next plot, I used a different y-axis. I was able to switch that very quickly, and you can see the variance is different, but you have a general sort of plot capturing some of the extremes. Then I tried scatter plot of the same exact data, and you can see there's a bit of a linear relationship with a little more spread on the bottom left. And just for fun, I did a heat map. So heat maps show the seasonal cycle throughout each year, and you can kind of see when you have highs and lows as you go across the years. So it's kind of an interesting sort of plot. And again, you can upload your own time series to do that. And we have a whole bunch of pages at PSL. And there's some other ones out there like Real Climate, if you ever heard of that, and KMNI. Next. Okay, publications. Plot should help tell a story. That is very important. You just don't want to, do plots of the different parts of your paper. You want it to be useful. So you want to prioritize accuracy and clarity, maybe not so much beautiful, but you want to get everything in there. They're meant for a somewhat specific audience. So hopefully they'll be interested just for the content. Again, you want to ensure reusability. So you can produce the plot again if you have a different data set or the data set extends and so forth. Most of the necessary information should be either in the plot itself or in the caption. That people tend to pull images or plots from papers. They tend to be the most remembered. So you want them to be very clear. You want them to have all the information. You don't want to have people have to go back and forth. So sometimes that means annotating plots, and sometimes it means improving the captions. As I said, next slide. Okay, so I gave here's an example of one where I thought could use work. I just clicked forward, look through some papers. I always call these eye test plots. it is hard to tell the difference between the various plots, and I'm not quite sure why they're showing it. The labeling on the plot isn't terribly clear. You don't know what experiment 1 or 2 is, and it's not in the caption. They don't define all of the details. For example, is winter GJF or is it October through March? You don't know that. The models aren't fully specified. It'd be nice to have a little more detail, like the source of the model in it. So that's just one example of something that could probably be improved. Next slide. So talks, there you want to have simpler plots with clear captions. People can't read stuff that's very detailed, especially from the back of the room. You want to label your plots the captions very well. You want to people be able to pick that up in a few seconds. You don't want them to have to read through 3 or 4 lines to get that. Avoid stuff like patterns, which might work in papers, but online, but on a screen, you probably won't be able to see them. So anything that's just hard to see or noisy is probably something to be avoided. And choose your colors carefully, which of course has been talked about. Again, consider accessibility like color blindness, but there's other things you might want to consider for that. Next slide. Web pages. Oh, I think I'm missing a slide. Anyway, I'll talk about the web pages. Web pages should be very clear, very well labeled. They need to have the name of the source because they're often downloaded from the web without the context around them. So people will create plots and think, oh yeah, everybody's gonna, save the whole page, but nobody does that. People just save the plot. So in this case, I'm showing one that works pretty well. It's very well labeled. The source is on the plot, PSL series. It has the complete names of the models. It has the complete description of the climatology. Abbreviations really aren't used except for the model name. So precipitation is spelled out, not precip or something like that. So that makes it, if somebody downloads it, they know what it's saying. And believe me, these plots do get sent around, and sometimes you hear back much later that there was some problem with the plot. So it is very important to put the source on there. Next slide. Okay, more on plots and visualization creation or generation. Next slide. Okay, writing code, seek out existing libraries and examples. You don't want to reinvent the wheel. Life is too short. Don't use default settings in programs. So you can often recognize a program produced in Python or Gravs or MATLAB or whatever, because they sort of all look the same. So they make all the plots reasonably well, but not terribly well. So for any particular type of plot, you want to change the settings, ideally, so that that plot works out the best, that type. So if you have a time series, you might want to make the lines thicker or that kind of thing. So don't just use the defaults blindly. Make code interactive. If you have code, you want to be able to read in different parameters so you can produce different plots without editing your code, which is always a pain. Share libraries, avoid hard coding. These are all things I've learned through time, and I wish I learned better because even now I make those mistakes, but it's important to try. And people are probably pretty familiar with the various codes, applications I've listed here, Python, MATLAB, and so forth. They all have the similarity that they have fairly large user bases. So you can have both help and examples of code. And often they'll have mailing lists if you run into problems, or they'll have web pages describing how do you install it, how do you use it, and so forth. So it's important to be familiar with that and to look for mailing lists and so forth if you need that. Next slide. Best practices. Some of this is redundant, I'm sorry. So reuse code, save the data independently. Actually, it doesn't help to reemphasize that. Try to avoid abbreviations, like I said. So people will often use the model values like TAS, the surface temperature, but very few people know what TAS is. So you want to try, even meteorologists will kind of know, but they'll have to figure it out. So try to use a real human words when possible. And this is particularly true for if you're plotting from net CDF files, where there's a lot of attributes, but the attributes often are for computers and not for people. So you want to make sure you use the term in a human sort of way. So let's see, what would be an example? Like using the standard name air underscore temperature underscore surface is a odd looking name to see. You just need to write that in sort of English. And try to keep to the same choices that people use in your field in terms of colors or units and terminology. And that makes it more understandable across the field. Next. Color considerations. Hillary talked about this a bit. Obviously, you have to worry about colorblind, and there's various pages you can look at that. Coming up with color tables, there's a bunch of resources. Sometimes some projects will have their own color table. For example, reanalysis has something called SRIP, which is colors that they'd like you to use for plots. And so sometimes you'll be in a field which does that. One thing that can happen when you use colors that aren't rainbow is that some people will use I think it was sequential, but older readers, older people like me, will often have trouble with the contrast of the colors and can't really distinguish between very fine shades for a particular color. So it's something to keep in mind when you generate these plots. When you're trying to avoid the rainbow, you do want to make sure it's readable for everyone. And of course, color should match the concept if you can, and unimportant differences shouldn't be represented by intense colors, things like that. So just beware that your colors will be interpreted certain ways by people. Next. Plot design, highlight features if you need to, put arrows and stuff on, but use as few as possible, but use as many as you need. Maintain consistent scales across plots and within plots. This doesn't happen in our field too much, but avoid volume-based distortions, like for area versus radius for circles or things like that. Your mind interprets volumes in a certain way, and areas and lines in a certain way. So you don't want to distort your data that way. Add contrast, so don't use pastels. And again, reduce unnecessary elements as much as possible. Next. Okay, so here's some bad plots. Just decided to show I found on the web. The top left one shows you a problem with scale. The plot on the left is linear XY, and the plot on the right is not, and it tends to make it look very steep. The bottom right one, the grid lines aren't needed; they just get in the way. You could get rid of them pretty easily. The bottom left is just scary, so we won't talk about that. But don't do that anyway. And the top right one, you're showing the line plot compared to a bunch of other plots. When you use all the colors, it gets very hard to see the plot that you're interested in. So you want to make that one more obvious. Next. There's a famous guy named Edward Tufte who did a lot of writing about producing really good scientific visualizations. I invite you to go look up his books in the library. He has all in many different fields, and he's kind of a bit of a cult figure. But he calls something chart junk, which is basically extra ink. So again, you want to remove anything that's non-essential. The more you remove, generally, the clearer your plot is. So on the bottom left, I have an example with horrible chart junk. Somebody called this one of the worst science visualizations they have ever seen. Not great. Over here, you can see the plot on the pink one on the right has a lot of lines and colors and other information that don't really help with the clarity. And so if you look at this one here, it's much more clear and you can understand it quicker. Next slide. This is something that comes up especially with web pages where you want to try to create a very high resolution plot. So there's various ways you can do it. You generally want to use lossless, not always, but especially for graphs. There's a lot of tools available to help you do conversions. ImageMagick is probably the best, but there's other ones too. And you can convert PostScript to Ping and so forth, and at a very high resolution, which is ideal. You want to remove extra white space, that way, especially for the web, that way you can position stuff the way you want, and you can fit more plots and so forth. And you do want to understand the difference between DPI, or dots per inch, versus pixels, and that's mostly for the web. And we have information about that in our lab if anybody's interested. It especially comes up with Python programmers because they deal with DPI. Next. Sharing your work, use GitHub, share all your code, maintain repositories, maintain reusable elements like watermarks for your plots to identify them, or standard color schemes. Makes your life much easier if you don't have to make those kind of decisions. Next. And I put some resources up there. There's more, you can put more, but there's lots of YouTube videos and so forth on making plots, lots of blogs, lots of libraries, and there's some here, but you can Google a lot, and they're all pretty useful. Thanks. And were there any questions, or should I look at them? Okay, I think that's all.
Well, thank you. Those are two tough acts to follow. So my my talk is actually going to be over in Google Colab, is what it's called. So if someone could dump that link into chat, and there it is already. I would encourage you, if you're interested, to click on that and follow along. If you're feeling particularly adventuresome, you can try that QR code, but that'll probably pull it up on your mobile phone. And if anyone's tried looking at Python code on a mobile phone before, it's a suboptimal experience. So the link in chat is probably your best route. So I'm going to see if I can share my screen here. See if I can find the right screen to share.
All right, we see your screen.
That's always a good sign. So Google Colab. I don't know the background of this audience all that well, so we're going to keep things fairly high level. Don't be afraid of Python. In fact, you don't need to know anything about Python in order to really run through this. From the link here, you can see that this is sort of a combination of some explanation, along with these little code, what are called cells. Hopefully each of these cells has a decent background. At the bare minimum, really all you need to know is if you go up to this runtime menu and hit run all, at the end, if I just scroll down real quick here, don't worry, you'll end up with a nice, well, hopefully a nice plot of real-time earthquake information. So we'll go through how we got there. But each one of these little cells, they're called again, you can basically just push play next to it. That individual cell will execute, and then you can see the results. So the way this operates, Google is actually giving you a free computer when you click on this link. So it's a virtual machine that runs in their cloud, but it's temporary. So the downside is that you, at the beginning, have to install all the software that you're interested in. So we're using this package called ArcGIS. ArcGIS is made by a company called Esri. I believe both NOAA and CU have a fairly sizable site license agreement. So it is free for everyone probably in this group to use. I should also say that we're only using free elements within this Python notebook. So in fact, anyone, regardless of whether or not they have an ArcGIS license, should be able to use this notebook to generate data. So this first cell, unfortunately, takes about 5 minutes to run and execute as it installs all the software that's required. So if you've actually grabbed the link and are firing this off, go ahead and hit play on that now. You can follow along with me, and hopefully, in about 5 minutes or so, if you want, you're welcome to tweak things. I've already run that cell, just to show you what that output looks like. Again, this is not meant to be scary, but the gist is essentially it's going out onto the internet, downloading all this software, building it, and at the end of the day, you've basically got the software stack that you need installed. A few things here up on top. ArcGIS, in addition to the software that they provide, also has this thing called Living Atlas. And we're using that as our data source today. So clicking on that Living Atlas link, it's livingatlas.arcgis.com. You can see a whole bunch of, literally hundreds, if not thousands, of different data sets that we could potentially load in here and visualize. So for today, we're looking at real-time earthquakes, but just to show you another example, here's the current weather conditions around the globe. Based off the METAR systems, which run at airports, amongst other places. And so we can get a sense of what this data looks like, do some interactive mapping. Boy, that's interesting. Maybe zoom in a little here. So you can start getting this idea, we're looking basically at wind speed here. But if I click on one of these points, in many cases you can drill in, get a bunch of additional information. But these are the data sets that we're looking through and accessing as we get into some of the details here. So like I said, we'll be looking at earthquakes today. We just looked at some real-time weather. They have information on current hurricane and typhoon tracks, wildfire information. There's a ton of different stuff. So we basically went through, we've installed.
Hey, Eric, we have a quick question.
Yeah. Oh, awesome. And thank you for paying
Google
attention.
Colab cost money?
It does not. So there are options for quote unquote pro versions. If you're a machine learning expert trying to train an AI model, you may find that Google is not going to give you the resources that you need. For everything we're doing here today, we're well under the threshold of needing what's called a pro account. Those do end up costing money. I've heard through the grapevine, at least within NOAA, since we do use Google for a lot of our infrastructure, there's talk of maybe getting some of those higher tiers. If I go into File, let me see if I can find this real quick. Notebooks, sorry, that was Edit Notebook Settings. You can see that some of these GPUs are grayed out and you can purchase additional units. We don't need to do anything about that. So yes, everything that we're doing here it should be entirely free.
Great,
hopefully
thank
that
you.
answers the question. All right, so we've got our environment installed. I'm going to hide that output. I've already done this as well, but after you install a whole bunch of software, sometimes it's a good idea to turn off and turn on your computer again. For those of you that use Windows, you're probably familiar with this. Anytime something eventful happens, it tells you have to restart. That's exactly what we're doing here. Just a little background for those that are not as familiar with Python. Think of Python as a Swiss Army knife. You've got a bunch of Legos. You don't end up writing a lot of code because a lot of that code has been written for you. So for example, a lot of our plotting routines, we're just importing here. So anytime you see an import statement, you might think of this as an include if you're into other programming languages, or just think of this as a reference, a citation. You know, we're basically pulling in a whole bunch of code that we don't have to worry about or maintain. As long as we use it correctly, it does a bunch of our stuff for us. Okay, so now we've set up our environment, we can actually get into the nuts and bolts. And the first thing is to connect to this ArcGIS Online. That's where the living atlas is. So I'll just hit play here and see, you can see it, okay. It's basically, I'm printing out information about this thing that I just created. And once I've created this GIS, I can start doing searches. So this then is connecting to the data catalog that's on ArcGIS Online. So you see I can do some recent earthquake queries. I could also just as easily, we'll do a query for fires. I haven't actually tried this before. I'm going a little off script, but that's good. So you can see there's something in here about beers. You know, this is thermal hotspot fire activity. So if anyone's seen an active fires data set before, this is likely where this sort of thing comes from. But as I mentioned, we're focused on real-time earthquakes. So we can come up with earthquakes, and at this point, we've got a few interesting data sets that were returned as part of this query. You know, I'm not going to get too into the Python, but if anyone has questions afterwards, you're welcome to contact me. I can get a little more into the syntax. But for today, basically, we're going to take a look at a little more depth. You know, so we have this display capability where we're basically pulling out additional information. So this shows a bit about this particular service. You know, pulled up a couple other ones. But just to kind of show you what this looks like, we're going to take a look at that first data set, this recent earthquake data set. And I'll pop over and take a look at the web page over on Living Atlas. And, you know, we could just open this in the interactive web viewer real quick so you could get an idea. So, you know, size basically is the magnitude. They've added some nice labels. We're not going to worry about shake intensity today. That's another way of looking at earthquakes. But if you quickly want to kind of see what it is that you're looking at and get a nice visual, referencing this URL is a nice way to do that. And that's based off this ID that's getting returned. But since we're talking about science on a sphere and creating visuals today, what we're actually going to do is download that data and then use Python to plot imagery which is compatible with science on a sphere. So first things first, we're going to go ahead and retrieve some specific data. So this ID is equal to the ID that came up above here as part of our search. So when I run these cells, it should only take a couple seconds. And another one, we can actually get a table of the output here. So again, not to get too into the weeds, but I'm hoping most of you are familiar with a straightforward spreadsheet, you know, Excel, comma delimited file, what have you. In Python lingo, this is a pandas data frame, and specifically one that's geospatially enabled. But the net result here, think of these as rows and columns. An important column for us in this case is going to be this magnitude. That's the size of the earthquake. And then we might also care about things like event time, in other words, when it occurred. There's a whole bunch of additional information in here, which I think would be interesting for plotting, but we're not actually looking at today. So for example, this alert, this is actually based off the economic and life impact of a particular event. So when you see greens, that usually means that not a lot happened as far as economics or death, always a positive thing. But then there are other categorizations as well. So again, not going to get too into the data, but the point here is there's a lot of information because we're not necessarily looking at imagery here yet. We're looking at what's called a feature layer. And that basically means it's going to be a whole bunch of points, as you might imagine, on an earthquake map. And then the next goal here is to plot those. So we've got our data. The next thing we might want to do is to find out the date range. So in other words, we might want to know that the information in this plot is going to be the last 90 days. So December 27th through, well, that's today. So we'll go ahead and create that function. Whenever you see a def like this, that basically means this is a little function, and then you can see in the next cell is when we're actually running it. So we're passing the data that we downloaded from the service into our date range function and asking it to print it out. And you can see that the information that was downloaded is, in fact, the last 90 days up through today. So this is quite current information. So at this point, we've got the data downloaded from ArcGIS. And the next thing that we want to do is to visualize it. There's hundreds of different ways of doing this, but the way I ended up doing it was I want a base map for this picture. The data itself does not contain any sort of base map. It's just information on earthquakes. So I'm popping out to an S3 bucket, basically a website, and asking it to download this image locally. So just to kind of show you what this looks like, after doing that, you can see I've got a little base map on the side here, which is pretty generic. This gets back to some of the best practices of, for this particular story, it might not help to have topology or terrain. The base map can be distracting, so keeping it minimal, I would argue is a good thing for this data set. So once we have that base map, here's our function for actually plotting the earthquake information on the base map. And I'm not going to get too much into details in this. You can kind of see some of the different steps, setting up the projection, adding the image, making sure the data is clean, that there are no missing values or attributes that might throw things in the way. Plotting the earthquake, we're going to add the label onto the map and then show it out. So I'll go ahead and play that, and just to prove that this is all real in real time, we'll run this and hopefully, excellent, we've got ourselves an image. And this image also incidentally saved out as a PNG. So if I click this little file icon over here and go to the map, this is where you could actually download this and have it locally on your machine after you give this computer back to Google. So you can see our label there. Always nice to label the date information. So this is the last 90 days of earthquakes. The color and the size here correspond to magnitude. Now, we could have gotten more complicated. There was that depth field. And so the version that was online, I think color corresponded to depth and size was the magnitude. You could slice this 100 different ways. Another thing to do, rather than create one image for the entire time period, we might want to slice that up and have an image per day. And then you start getting sort of this popcorn effect of where earthquakes are happening more frequently. So this is meant just as a starting example, but hopefully you can see how this code could be modified, complexity added, et cetera, to have it point at other data sets or to generate animations rather than just movies. And then finally, it's always nice to have a legend. In the land of science on a sphere, typically we keep our legend imagery separate from the data and then display it on the sphere as sort of a picture-in-picture. So separate function to create our earthquake magnitude, and there is the legend that we're using. I chose a color map that's called Inferno. There are literally thousands of color maps out there. This one I happen to like. It's color safe for the most part, colorblind friendly, and perceptually uniform. So in other words, if you convert this to grayscale, and take a look at it, you can see it's pretty much black on the left and close to white on the right. So this color bar works in pretty good context. I actually didn't know before putting this Python program together that magnitudes could be negative. So I learned something there. I thought that was a mistake, but looking at the data, yeah, there are a bunch of negative magnitudes. And apparently things like around -1 are the equivalent of like a book dropping off a bookshelf. So, this falls well into the range of sort of man-made vibrations. But yeah, that was a very quick overview of doing something using Python in Google Colabs, and maybe we got a couple minutes for Q&A.
Anyone feel free to put questions in the chat or come off mute. We do have one more, Eric, in the chat. How do you know where to look for the base maps?
That's an excellent question. I've actually got a library of them at this point that I'd be happy to share for those that are interested. Esri, ArcGIS, some of their data layers are actually base maps. So just off the Living Atlas, I think you can probably grab 15 or 20 different versions. And of course, the base map should help tell the story. So if it's ocean-based, they have a lot of good ocean data sets. Yeah, you have to look through those. But if folks are interested, I could certainly point you to a collection, or at least for the Science on a Sphere program, I know we've got quite a few. So if you're looking, let me know. Base maps are complicated too, because with global data, they can be a reasonable size, but if you want to zoom in to a particular section, for example, if we want to highlight Colorado, you might need to go out to like a tile service and stitch together a base map for Colorado, or you have a very high resolution image, which you can sort of crop down to the section that you need. But it gets complicated. So I kind of intentionally glossed over that today, to be perfectly honest. The dark gray base map that you saw there, I want to say it was a 4096 by 2048 image. We've got another version, which is, upwards of 40,000. And that one I use in areas where we want to zoom in to a particular area on the globe. Any other questions? Well, I hope at least some of you tried to follow along on your own copy. One thing I didn't mention, you're welcome to go to the File menu and then save a copy in Drive. And that way you'll have a copy of this Colab notebook that you're welcome to take ownership of, edit it to your heart's content. If you come up with something cool, please consider sharing, because it's always interesting to hear what other people come up with.
Thank you, Eric. I sure learned something. All right. Any questions for any of our speakers? All right. Well, then I have a quick request first. Everyone to thank you for coming. We'd love to know what you thought of our training. So we can, we have this survey that we'd love to get. It should only take a couple of minutes. Feel free to, if you think of any questions in the next few minutes, let us know. The recording will be posted on the website I referenced earlier, and so will the slides. So if you want to access any of the resources and the links that were provided within the slides will be accessible to you, and I'll send out an email afterwards as well. All right. I'll give another couple of minutes if anyone thinks of any other questions, but a big thank you to all of our speakers for participating today, and really appreciate all of your expertise.